get started. This is the final talk then in the 50 years of Satisfiability workshop. We have Sasha Razborov speaking. Great pleasure to have him here. He's of course got extensive contributions on the theory side of complexity, that and other areas. But I think it sounds like he's talking on a more applied topic today, illustrating the interaction between theory and applied, but we'll find out in just a minute. But he's talking on time and space and depth and width. So thank you.
All right, so thank you very much, Sam. The first thing I was going to say that it will be a purely theoretical talk, unlike the previous one, but I feel I should not let you down. I will try to make at least something out of it. And actually, it is quite applied talk in the sense that I believe that no one, that people in this workshop at this time, they need not be convinced that proof complexity is important, and particularly those parts of proof complexity that deal with weak proof systems like resolution, and resolution will be the main hero during this talk. I will skip all the motivations. And indeed, at least I believe that all complexity measures, main complexity measures we study in proof complexity, they somehow, maybe not directly, maybe they look different when they go to the practical domain, but still they correspond to something in the practical world. And it turns out when you start doing these things, then something very strange happens. Complexity measures and concepts about propositional proofs that when they were defined, they really did not have, it was not clear whether they should be somehow related to each other. Turns out that there are very many relations. And that's the picture from our new paper, where we tried to put on one in one place what is known about those relations, and actually my talk will be mostly to explain this picture. So it's cool and it's unexpected and there is something behind it, and in many cases we really don't understand what is behind it. So let's start slow. So I believe that at this point, I don't have to tell anyone what is a resolution proof system. So just in case it is here, the weakening rule is cosmetic. It's not here, but if you want weakening, you can take it. It's not important. So so can you see my mouse, Sam?
Yes. The mouse is up. Yeah.
Yes. So I think the only thing to get from this slide, the only message is the notation SR stands for the resolution size, and that's our picture. There is not much on it so far. So resolution proof size is absolutely at the bottom. So everything else, in a sense, will be just a relaxation of resolution size. And as you can see, I take log. We will see soon why it is natural and important thing to know. So in order to compare apple and oranges, you should have apple and oranges. Let's compare apples and apples first. So this is the second in importance probably proof complexity measure for resolution. So, I mean, it was defined by resolution, but if you think about it, then there is nothing about resolution here. You simply, if you have an arbitrary function or an arbitrary constraint in W variables, then you can always express it as a set of classes of curves. So it's inherently semantical measure. It simply means that all concepts you use in your proof or in your algorithm depend on at most W variables. So, and it is the obvious observation. It's simply based on the fact that the right-hand side, it is a bound on the overall number of classes of width W. And as I said, I prefer to take logarithms everywhere. So, and when we take logarithms, then we see that log of resolution size is roughly W, only we have here this new log n factor. So one thing I'm going to argue today about is that if you consider proof complexity measures in this region, then it is very natural and very, when you start doing things, then you see why it is natural, is to allow both log n factor and polynomial overheads. Then the picture really becomes structural and it becomes very nice. You can just see that things come together. So it is clearly, well, it means obviously that mu1 is smaller than mu2 and mu2 is smaller than mu1. So one remark is that it is distransitive, which is good notion of simulation, and another remark is that normal size measures will appear today under the log sign, which means that in the standard Cook-Rakov framework, it corresponds to quasi-polynomial simulations. Well, it's not the main focus of this talk, but I would perhaps like to mention that we see in proof complexity, we see quasi-polynomial simulations coming up naturally in many different contexts. Like there's been a recent great paper on cutting planes and stabbing planes, and you see that quasi-polynomial comes in very naturally and maybe not for not so dissimilar reasons to us. Anyway, that's our main concept of simulation. Then, of course, this means that SR is log SR is at most width. Let's put it on the picture. Right. So now we have at least something here. And of course, we know that this is proper. It is these two measures are separated in the strongest possible sense. It is the result by Bonnet and Gallesi 20 years ago, and it was meant as a separation for Bensason-Wigderson simulation, but Bensason-Wigderson it is not in this framework. If you know what it is, because it has extra n factor, and we cannot afford n factors here. I mean, n factor in the exponent. Right, good. Let's move on. So the next station or the next stop is tree-like resolution size. Well, in this community, well, again, I think most people know that tree-like resolution corresponds to DPLL. You cannot do too much with DPLL. You have to do other things, but still theoretically it's a nice and important and interesting model to compare with things. So an easy part of Bensason and Wigderson, it says that, well, I mean relatively easy, it says that W is at most log tree-like size. And if you are wondering, usually when people state things like that, they put the width of the original CNF to the right-hand side. I don't do it, first of all, because I cheat. And second, because in our new paper, you can see that how can you slightly redefine things that you will not need this annoying term, or you can simply assume that your F has constant width. Whatever you like, I will not put anything on the right-hand side here. And it was also proven to be basically tight. So in the first paper, they did here n to some power, and then it was improved to almost optimal. So now we have the relation between width and logarithm of tree-like size. That's where we are now. So far, I'm talking only about apples. Apples means size measure ordinary proofs. So depth. Depth is also known in the logical community as height. You have a proof, be it DAG or tree-like, and you look at the longest path in this proof, which is defined just in computational complexity, of course. And what is obvious, this simulation is obvious just because if you have depth d, then you can somehow make it into tree form. You can split all branches, and you will get a proof of size at most 2 to dd. So what is somewhat surprising is that this is also tight. And I say surprising because, as you know, in complexity theory, if instead of proofs you talk about computations, then it is tight. It is called Spira's theorem, and it is one of the most basic results in circuit complexity. That if you have a depth, low depth computation, then you can make a formula, small formula out of it. So it turns out that in this world it is precisely the opposite. And here I would like to at least mention some of the most important topologies or CNFs that are used for separations in this. In this business, it's Horn formulas called Veblen contradictions sometimes. So we have a DAG, say with one source and one sink, ST DAG, and we form basically this Horn formula, which is written here. We simply say that if I have proved x1, x2, and x3, if I have proved all immediate predecessors of x4, then I can infer x4 also, and I start with S, and I want to refute T. And the simple observation is that the tree-like size, resolution size of the refutation of this formula is at most n, which is written here. And it means it is simply because I just infer these variables one after another, corresponding to the vertices of this DAG. And Urquhart proved that the depth of this sink is bounded from below by the black-only Veblen complexity of Gn, and since we know that there are binary, meaning Frennin's graphs Gn with large Veblen complexity, it also implies that the separation between those two measures. So what else can I say here? So it turns out, and I believe it was introduced in our paper, that it is convenient and we need it. We will need it for one of our results. What is it? It is convenient to introduce another measure, complexity measure, which is positive depth. We call it positive depth. So it actually means that whenever we have a resolution refutation, then we go along this branch for free. For free means that I don't increment depth, counter for depth. Depth gets increased only on this branch, on this branch. So why it is called positive, of course, because in the implementation, if you view it as I don't know, an algorithm, then it corresponds to assigning x to 1, not to 0. We want to falsify this thing. All right, good. So it will...
Question?
Yep.
Yeah, so the number of negative literals, do you mean the number of times you have resolved on a negative literal clause or just the total number of
it's tree-like.
It's tree, yes.
So it does not, you can assume that it's regular.
Okay, so you assume it's regular.
Yeah, okay. It's about depths, so we can assume that it's tree-like. So, and it's local, it means that it is maximum number along a path. So if you look at this thing, then it's not clear that it is even non-trivial. Right, looks like we allowed ourselves lots of freedom. Maybe we get something stupid here. It turns out that it is non-trivial. First of all, one obvious fact is that it is, of course, smaller than depth. We count less things. And less obvious fact is, but very easy, is that actually it is larger again within the precision we tolerate. It is larger than log of tree-like size. Let me just show you the proof, because this recurrence, this recursion, it appears over and over in this business. It appears many times. It's the same recursion. So, and it's very easy. So if I want to bound the tree-like size in terms of the number of variables and positive depths, then as we did on the previous slide, so I simply recurse according to the resolution rule at the top. And along good branch, we have that both positive depths and n decreases by 1, but something happens even along the bad branch. We don't increment positive depths, but the number of variables drops. So we have this recursion, and you know what it converges to. So again, this kind of calculation or computation appears all the time in these things. So, and the observation, it stands for negative. You have to negate things, but anyway, the observation is that if you look at Urquhart's proof, then it actually separates positive depths from both depths and tree-like size. Both these things are optimal. So it's very easy to see. Let me skip it. So now we have all apples on our picture. So it's a nice hierarchy where we can separate everything of resolution proofs with resolution proofs. So apples look great. Let's now talk about oranges, because that's what is interesting here. So somehow when you talk about proofs of the same nature, it's somewhat not very surprising that they are related. What is surprising is that when we completely change the gears and talk about space complexity, then we still have lots of relations. And we will see it. Right. So this bunch of definitions, I again believe most people here know. It's space complexity. It's captures the situation where we really care what we keep on our whiteboard or in our memory if you run CTCL, for example, solver, whether it's erase something or not. And the general definition goes like this. So almost always it will be just a set of clauses, but I don't want to commit myself to it. And we have just these 3 rules. You can either download your original clause or an axiom into your memory. You can apply inference rule. It's written here for resolution, but you can do it everywhere else. And you can erase something just in this way. You save on memory, and you can reuse memory for other things after that. Again, so it's well-studied class of models, and a configurational proof is just a sequence of configurations like that. You start with empty set of formulas, and you want to infer a contradiction, And you measure complexity of a configuration, what you have in memory at every particular moment, and also then the usual stuff, the complexity of a refutation will be the maximum over all these things, and so this will be the minimum over all refutations. So it is, here I go over those complexity measures that will be needed for my talk. So, and there is a bit of terminological confusion here for which I am partly responsible. So let me just state here, class space is uniquely defined is the number of classes you keep in your memory at every particular time. Variable space is the overall number of variables you keep in the memory, and with repetitions, which means that if one variable occurs several times, you count it only once, and if you count all variables in classes in a given configuration into as many times as they appear, then you will get just the bit size, which is called total space. So these are the measures that I will need. All right, and very interesting results. And so then all of a sudden turns out that these things defined totally differently from our first part. They turned out to be related. First of all, it's not chronological, or it's great result that bounds width in terms of class space. Again, I skip everywhere this annoying term for good reasons. And in the original paper, Esteban and Toran showed that it is bound by log st. And by the way, you don't have to rush and read my formulas on the slides. It's mostly for the records, but everything will be shown on the picture, of course. Essentially, it says it separates W from class space. Turns out that separation between class space and ST is a major open problem that we will discuss in the rest of my talk extensively. Okay, so and our results, let me know that it is very weak because I don't have log here. So it is what it says. Class space is constant, and we can come up with tautologies where tree like size is at least quadratic, and you can improve it or generalize it. So you can put k here, and then it will be n to dk. But still, it is extremely weak. But that's the only thing which is known in terms of these results, how tight it is. At least we believe so, and also. And it is for this proof that we need positive depths. It comes in very naturally. All right. Okay, so now that's what we have. We have introduced class space, and for some strange reasons, it is between these two respectful measures, and now we don't need this thing. So it follows from what is here. Let me, before I will, so I have two more things to discuss. Let's talk about variable space. So variable space, it is obviously bounded by width because both of them talk about the same thing, the number of variables. If I have variable space, then it is simply all classes will have width W, at most W. You will have a proof of this complexity. So Urquhart also proved that it is bounded by depth. And Ben Sasson, in his very actually interesting paper of 09, he did not he didn't talk about positive depth. He was talking about class space here, but if you look at, so he separated variable space from class space, but if you look at what he did, how can you easily adapt his proof, then it goes up to positive depths. So, and it was actually earlier than the result by Urquhart I mentioned before, but it's way more difficult, and in particular it uses black-white pebbling. In order to bound variable space, you need to have black-white pebbling, not only black pebbling. So here is where we are now. And again, here is we have one more red arrow here because we don't know how to separate these two things. So, and let me also say something about monomial space. Monomial space is our first model which is not based on resolution. Namely, in resolution, we still have a set of classes in my memory. It's a set of classes. So, but in resolution, we simply think about it as a conjunction. We simply say that, semantically, what is in the memory, it just says that all these classes are true. So, in more general model, what we have that the semantical content of my memory M, it is determined as an arbitrary function f in the set of those classes. And so in the most general model, it can be essentially everything, but the model which people are mostly interested here in this context, it is called polynomial calculus with resolution. You fix a field and you view at these things at negation of classes as monomials over that field, and that explains the term monomial space, and you can write down a bunch of polynomials with those monomials as terms. So anyway, all results that I am going to mention, they are true for an arbitrary, for functional calculus. You can put everything in the memory as long as it is a function of classes. And now what we have here, we again have this, that first of all, the obvious observation that is that this thing is below class space. And a very interesting observation, not observation, it's a deep theorem, is that actually, again, for some unclear reasons, we have that W is smaller than M space after a square. And an interesting open question is whether this square can be removed. Because it will give lots of things. It's much easier to get lower bounds on W than on M space. And in the opposite direction, we do not have a separation. So the best thing, as far as I know, in terms of separation between W and M space is this work in progress. So it gives you a quadratic separation, and quadratic is not enough for us. All right, here, this is where we are now. And, so let me, this arrow goes away, but more reluctantly, because it still carries information. We can separate width and closed space, but we cannot separate. We don't know which one is different. All right. So now I have to explain the other stuff. Most of it is start. So let me start with this analogy. The motivating question is if you have a limited space, then for how long can you survive telling different stories? And if you like science fiction as much as I do, then people speculate what are the difficulties in building a spaceship that goes from Earth to some distant star. And one part of the speculation is that the space in your ship is very limited. And the space is very limited and people tell stories. And at some point they run out of stories become too repeated, it creates psychological problems. So I know at least one or maybe two pieces of science fiction that speculate about this thing, so that in very limited space, you really can tell only a bounded number of different stories. So in our framework, we have, it seems that we have very long proof. Certainly, if stories start repeating themselves, if mk is equal to ml for different knl, then we are obviously in trouble because it means that we did not make any progress. The part between mk and ml is lost on us. We did not do anything, it can be removed. It's not good when stories repeat themselves. And how many different stories you can tell? These are the bounds. So it is exponent of this thing is the obvious bound on the number of a family of S classes. And so it is everything you can express as functions in S variables. And here it is simply because if I give you S variables, then you have 2 to the S different Boolean functions. And in red here, there are problematic terms why it can be large. It can be large here because even when S is constant, you may have many different configurations, and here you can have many Boolean functions. And the question is whether it can really happen, because stories they should be meaningful. They should be our proof. They should be a part of our proof. And the best way to ask this question is to introduce this variance of complexity measures. If I have space complexity measured, then instead of just measuring the complexity of my configurational proof, I amortize it or regularize by log of its length. I penalize for particularly long proofs. And then turns out that our picture, if you introduce this star, turns out that our picture becomes extremely much better aligned. So this picture is sort of imprecise, right? You have lots of measures and they move around, and some of them are comparable, some of them are not comparable. Turns out that if you look at the amortized versions of them, then everything becomes just very neat. So, and here is what happens. If you ignore non-start versions, then it turns out that amortized versions of everything, or at least of many things we are interested in, space complexity, they just fit our picture precisely. They fit one of these two levels, and there will be a third level. So that's the picture that you get. And now I have to explain a bit the remaining still yellow stuff on it. So let us do it. As I already mentioned, and I will actually, and the rest of my talk will be devoted to discussing this issue. As I already mentioned, it is major open problem for many complexity measures whether amortization really helps, whether really long proofs exist. So here is the only general fact that I am aware of. So you will be your complexity measure mu will correspond to both ordinary measure and amortized version. It will correspond to depth according to our relation. So in this case, if it is coming from a circuit class and such that it is intermediate, it is bounded from below by the number of variables and from above by the circuit size, according to this class. So total space, it fits here. Variable and class space, things we are most interested in, they fail this criterion. Variable space, it fails the second part. Boolean functions that you have in variable space, they can be totally non-constructive. They may not correspond to even unbounded circuits. And class space, it fails the first criterion. Namely, class space can be much smaller than the number of variables. So, and in the chain of inequalities in our paper, you also have regular and tree-like class space. So, and just a few words about the DNF resolution space that we also introduced. So, in this model, now it's slightly more complicated, one level more complicated. In memory, we now keep DNF formulas, right? Instead of classes, we keep DNF's formulas, and it turns out that it is convenient now we have to measure space. It is convenient to measure the space as the sum of widths of formulas in my memory. Why? Well, first of all, because this was studied in many, it was studied in at least several papers for the case of constant widths. So, and it was formula space and very consistent because then you're just up to a constant factor. It is just our definition. And of course, the main answer is that this awfully difficult and somehow complicated model turns out that it is the same as width period. Well, up to a certain. Actually, this part, it is surprisingly tight. It is simply the same up to a constant factor. It just describes widths. So, and I'm almost out of time and I still have a few slides. So let me show the last system. It was considered by Young-Krajcik. So it is the system in which the widths, it is a subset of DNF resolution in which the widths of all classes is bounded by a given function, like log function in the size. And again, for some reasons that we really don't understand, turns out that it will be tree-like proofs in this proof system are again the same as widths. And remarkably, I think, well, you can spoil any proof by making it direct, but our proof, these are so size measures, or at least measures corresponding to normal proofs. The natural way of doing it is to use sigma to space, at least in one direction. So that's the thing that actually occurs many times. And it's in all these things that if you want to prove that something is related, then it is better to use something else as an intermediate. It's how we do things in complexity theory, as well everyone here knows. All right, so it is just the repeat of my first slide. Now we are officially done, and now we know what all these things are about. And I think it's a nice picture. And it really shows that there is a bit of a structure. And now I am moving to the last part of my talk, which is basically open problems only. I will add a few annotations since in my view, and I think in view of many, all open problems are here on this slide. These are these thin red arrows. These are fundamental problems to prove that these measures, they are really separated. So let me make my notation. Let's start with variable space. So as you can see, given that we have really several big clusters, all the things are equivalent to other things. So first of all, it is the same as asking work-hard question, whether depth can be bounded by variable space. He did it in the opposite direction. And also, if you don't know what it means, I don't have time to go into details, but it means that you want to have a trade-off which is supercritical in the sense that low variable space proof must be really huge. And here is what we can do in this direction. So only quadratic separation, and the proof is shockingly difficult. And if there are here referees of my paper, I certainly see here the handling editor, then I just want to thank them for the work they did on it and apologize for its complexity. I try to simplify it, but somehow it's not clear how far you can do. It's awfully difficult proof. So the next, plus space versus amortized or plus space, and it's also either equivalent or quasi-equivalent. So a few of other questions. Well, the first clear question that was asked in the seminal paper by Esteban and Store on whether you can go in another way. You have a small class space. Can you get a small tree-like case? A small tree-like resolution refutation. It's all equivalent. Jacobs asked a question. So whether you can do this thing. So if you have small class space refutation, then by Atzerias Dalmau, you have a small weights enhanced polynomial size refutation. He asked, or Jacob, asked whether you can do it simultaneously. It's a great question, also equivalent to this one, and you can also phrase it as asking about supercritical trade-off between class space and depth. So, and I guess you can continue this list, since amortized class space, it really corresponds to many things. Then you can ask lots of things here, lots of things there. So monomial space and class space, I guess this question, some people at least here, they spent a considerable time on it. The only comment I can make here is that our structural picture, it explains some difficulties, because if you separate these two things, then you will also separate monomial space from its analog, from its amortized version, and we believe that it will be very difficult. That's the only remark I can make here. And the last error is that it is also quite embarrassing here, because, as I already mentioned, we have results. These are quite concrete, actually, variants of Pepling or just Pepling, tautology separating W from class space, and we really don't know what is monomial space for these tautologies. So you might think that you would be able to analyze them, and I guess the conjecture is that they are hard, but that's what we are missing. And absolutely, the last slide, I'm several minutes over time, so let me just say briefly that we have for resolution, which is areas of 1, we have one picture. For resolution, areas local resolution, we have another picture, and it is natural to ask what happens in between. This is what can be said from our proof, and the interesting question is what happens in between. And for example, whether tree-like, say, whether tree-like proofs in this proof system, they are the same as small formula space proofs in the same system. So that's the last open question, also of the same form. So, and that's basically what I wanted to say. There is a nice and rich structure here, and so it will be really interesting to fill in the remaining gaps because these are really fundamental systems. Thank you.
Thank you. Very nice talk, very thorough. So we have plenty of time for questions, so please speak up and ask questions. And
so in your amortized, your star definitions, I want to get a sort of more fundamental intuition of why you think of it that way, why you pick that particular formulation for the way of going from a space class to its star.
It's Paul, right?
yes, that's Paul speaking.
I cannot. I think I can manage to do it, but it works in many contexts. So it's a natural thing to do. First of all, as I said, Eli started it. He did not call it new star, but he amortized by this thing. And when you're just you're probably asking about why log, why not something else?
Yes.
What else? What else? It's either constant or log or just p, and it's the right size, and the main motivation is that it is the right regularization factor. Well, since I mentioned this word regularization, then let me perhaps also mention that we put here multiplication again because it naturally comes in proofs. After a polynomial, you can put here additions, and it will be just the normal regularization you use in learning theory, in machine learning. You can put plus here, and very little will change. Yeah, that's.
I see.
It works. There are actually no or almost no alternatives to it. And I think the best explanation is that you have this picture.
Sure.
It
clearly works well.
it works well, and there are only 3 possibilities, and the other 2 are ridiculous.
Okay. And why? I missed a basic point about that. Why is it called amortized?
Why it is called amortized? I thought it's the right English word, but when now you say
it is an English word. It usually means where you take like average cost over multiple steps, right? So you have an amortized algorithm, which means that sometimes.
Yeah. No, so now when you mention it, then I start having doubts by myself. Maybe regularization is the better word.
Okay.
Amortization. Yes, I think you are right. Maybe regularization is a better word. We punish for exceedingly long proofs.
Okay. Let's see. There's a comment in the chat window from Zaid Sawaf. Many theorems were cited from articles. How to get a list of the references?
It's all in our paper. It's very simple. So take our paper. It's on my website. It's or on Theodore's website. it is if you are on the proof complexity mailing list, then you got even a link, and all references that I have cited today are in our paper. It's very simple.
Okay.
And more connections because I had to skip something today.
Very good. And more questions? So I did miss earlier, you threw away some of your blue arrows where separations were known. Was that just to save space on the screen, or?
Which one?
Well, you had some arrows.
I think it got added again. The one on the
Okay.
right-hand side is
Yeah,
that
the one on
same
the
one on
right-hand
the
side.
left-hand side.
The
that
picture you
was
just
there.
had there, yeah, there's a lighter blue arrow and darker blue arrows. So that's maybe right there.
Here, yeah.
Yeah.
Well, it's here is light blue because we know inclusion, but we don't know separation.
Okay.
Oh, no. Sorry. I mean, what I'm saying, we have separation here, right? But we don't need the inclusion because it follows from these two things.
Okay. Okay.
It's like P space and exp time, right? We know that P is in exp time, but we can do it Y P space, and we cannot separate anything here. So, and many slides.
Yeah.
This one, we don't need it entirely because it follows from this thing, right? Both separation and
Right.
inclusion.
Mm-hmm.
And so this one, it is just So it's the same arrow from the first slide, and I just removed it here, not to make the picture more. So
But it showed back again.
it showed back again as a final result. So it's I think it is really embarrassing that we can separate width from class space, but we have zero idea which one of this is actually separated.
Right.
So anything else on chat, or it is the same?
Oh
yes, Mark.
Mark posted a link to your paper, small
Yeah.
space .pdf.
Yeah.
So if the people want that to look at the paper right now, they can grab the link out of the chat window.
Thank
Good.
you, Mark.
Mm-hmm. Any other questions, comments? It's your last chance to ask a question in the 50 years of SAT meeting, so don't be shy. And otherwise, if no one speaks up real fast, we're gonna wrap things up. All right, so thank you again very much. I clap on behalf of everybody. I think we had a wonderful set of speakers, including the final ones today. It's been a great experience to do all this. So thank you for all those who are attending. And before you run away, Antonina's going to post a GatherTown link in just a moment if you want us to talk informally in GatherTown for a few minutes.
Let me, I believe I should stop sharing, right?
Okay, good. Yes, we can see everybody now better.
I think I just did it.
And there is the town hall meeting in about 30 minutes also for after the GatherTown meeting. So we have plenty of chances to interact. And Antonina, do you have anything to add about the town hall meeting?
Not much, just can you see me? We'll start the town hall in about half an hour, and if people want to say something, please let me know. If you decide to say something during the meeting, you could message me or Andrea during the meeting. It will be fairly informal. Just what do we do from there now that the program is over? So hope to see you there in half an hour, and maybe before that on GatherTown.
Very good, thank you. And the GatherTown link is now in the chat window. So, all right, I think that's the end of this meeting then. So see you guys possibly in GatherTown, but definitely in the town hall meeting in 30 minutes for those who can make it. Good. And thank you again, Sasha and Armin, for the great talks today.
Thank you.